Yes, class. So in the last class, we had started with hydrodynamics and viscosity we had seen. So what was viscosity? Talha, you were absent in the last class, no? Did you see the recording? Talha.
Yes, ma'am.
All. So we started with hydrodynamics. So in hydrodynamics, now a fluid begins the motion. So when the fluid is in motion, what happens is viscous force will be applied. It means a frictional force will be applied in the opposite direction. Now, few small topics are there, and one major topic is there in your hydrodynamics. That is Bernoulli's theorem. So that I won't do it today. Today we have some other important small laws also from which questions can come. So let's discuss that first. See, you have Stokes law. Stokes law is valid for any body which is a spherical body. Like, let's say, water layers are there. Here a spherical body is there. So what will happen? Water layers will adjust themselves onto the sphere like this. So the viscous force that will be acting on the sphere. See, the radius of the body will be there. The sphere is moving. Condition is that motion should occur, because if motion does not occur, then entire hydrostatics which you have studied, everything, pressure exerted by liquid column, capillarity, surface tension, those will come into access. No, here motion should occur. So velocity, viscous force will act in the opposite direction of motion. Now this is just a simple single law, no derivation is there. Just remember it. The viscous force on a spherical body is 6, the constant number 6, pi 3.1422/7, which we write the constant pi, eta, coefficient of viscosity, radius of the sphere, capital R, and the velocity, v. This is the formula also, and we call this as Stokes law. So this is basically Stokes law is just this statement. All right, 6 pi eta RV. This is Stokes law. So you have importance of Stokes law. Importance of Stokes law means, first is that you in your class 12th, no, when you step up in class 12th in few months only, so you have certain chapters in the beginning only which involves electric charge and everything regarding electrostatics. So electric charge is measured using Millikan's experiment, oil drop experiment he did. He took oil drop in a medium and then saw whatever charges were required and all these. So Stokes law was important. He applied Stokes law. Then formation of clouds also you use. Stokes law is basically applied. How much viscous force will be applied? Formation of clouds, as in when the water droplets are moving up, there it is used. Then find the size of small particles, or why large raindrops hurt much more than small ones. See, the reason is that Fe is directly proportional to radius. Right, this is directly proportional to radius. This is also directly proportional to velocity. If you increase radius, if you increase velocity, your viscous force will ultimately increase. These are just the simple reasons. So this is all about Stokes law. Just the simple formula 6 pi eta RV is your Stokes law. You have one more topic, terminal velocity. Here a graph also come that I discuss. First note down Stokes law. See, now terminal velocity means, let's take an example. Let's say I have a container, and in this container, I have filled a viscous fluid. Let's say I filled it with honey. This container, I have filled it completely with honey. So honey is thick. Honey provides certain resistance. Even if you see, you can feel the difference between honey and water, how viscous honey is. So let's say I have taken a container and I have filled it completely with honey, or you can take glycerine. Glycerine is also slippery viscous material. Now what do? I will now take a small ball and I will now drop it. So let's say this first velocity, when I'm dropping, this is 0 meter per second. It is at rest, no? Now I have released it. It will move. Let's say its velocity will increase. Let's say it becomes 2 meter per second. Fine. Then it goes further down. Its velocity increases to, let's say, 4 meter per second. So can you see here it was initially at rest. Now it is increasing 2 meter per second, then 4 meter per second. But now what I'm observing, when this ball is now falling, the fourth velocity is also 4 meter per second. When it is going deep inside, the velocity is still 4 meter per second. So what has happened? 0 to 2, 2 to 4. But then after 4, this became constant. So the velocity which becomes constant after falling through a viscous medium, we call this as the terminal velocity of the body. This is meant by terminal velocity of. All right. So when you have a body inside a fluid, buoyant force keeps on acting upwards. Viscous fluid also keeps on acting upwards, and in downwards direction, you have the weight of the body. Fine. So this is meant by this constant velocity. Velocity is increasing, and it has reached a terminal value. Now it cannot increase more. And every body has its terminal velocity fixed. Once it is achieved, then the velocity's value will become constant. Now you have certain importance of viscosity. Viscosity of air or liquid is used in providing damping torque in the measuring instruments. Then oil is used as a lubricant. It should have a proper viscosity, and viscosity is also used in applying brakes. Hydraulic lift principles you must have studied, and we have also studied hydraulic lift. So in applying brakes also in vehicles, viscosity of oil only helps. And in the human body also blood circulation occurs. So that is also viscosity of the blood. Blood has a certain pH, certain viscosity. So that viscosity helps in the circulation of it. Fine. Now, what is the formula of viscosity? So this is the graph of viscosity. See, this is velocity versus time. Here I'm increasing the values of velocity. So at this particular time, velocity is this. At this particular time, velocity increased. At this particular time, velocity increased. But at this particular time here, velocity became a constant value. Now I'm increasing it further. The value is same. This is terminal velocity, which is constant. After this, let us just perform a very small derivation we have. See, in a fluid, what all things I have said. See, in a fluid, you have, let's say I have taken a ball. In this, you have an upwards direction, buoyant force, and viscous force occurring. In downwards direction, weight. Why viscous force is acting upwards? Because I have taken velocities downwards. Now see, net force will be what? Add all the upward forces, subtract it from the lower force. How do you write the net force? Look here, net force will be FB plus FV equal to weight of the body. What is weight? Weight is mg. Mg, or you can do, let's say density of body is rho. So rho Vg. Why rho Vg? See, density is mass by volume. So here mass will be equal to density into volume. So rho Vg. This is weight. Secondly, what do we need? Buoyant force. So buoyant force we have studied. V sigma g, volume of the body into density of the liquid. Sigma is density of liquid. Refer to buoyant force, all those who have forgotten what was buoyant force. And lastly, you have this FV, which is Stokes law you will apply now because spherical body we are considering. So if you're applying Stokes law, so this will become 6 pi eta RV. You have three terms, 1, 2, 3, which are essential. And this is the main equation that will help solve. So at a certain velocity, all these will be equal. So we can put in the values. So if I put in all the values, I'll obtain this V sigma G. Right. Now see, once this is done, once I have put in these values, this is what? This is buoyant force. This is viscous force. This is weight, right? Buoyant force. This is viscous force. This is the weight of the body. Right, now bring this volume terms together so that we can simplify. 6 pi eta RV, V rho G minus V sigma G. Take volume common. 6 pi eta RV volume, or take VG common. Both are common, rho minus sigma. Now from here, what is the value of velocity? Look here, class. Vg rho minus sigma by 6 pi eta r. 6 pi eta r till now, right? Now what is the volume of a sphere? Volume of a, see here, volume of a sphere is 4 by 3 pi r cube. This is volume of sphere. So put it here. See, so velocity will become, this is 4 by 3 pi r cube G rho minus sigma by 6 pi eta r. See, 1 r cancels the square, pi gets cancelled, 2 into 2, 3. So what is left? 2 by 9 r square, this G rho minus sigma divided by eta. This is the formula of the terminal velocity. This is important. Now, what all terms are here? R is the radius of body. Fine. R is the radius of body. Then you have rho as density of body. Sigma is the density of liquid. Eta is coefficient of viscosity. This is coefficient of viscosity. Now, remember 2 by 9 r square G rho minus sigma by n. Now see, if rho is greater than sigma, if this term is greater, I'll give you, write it separately. Look here. If rho is greater than sigma, it means rho minus sigma we have to use. Let's say density is 3, sigma is 1. So 3 minus 1 will be 2. If this term is greater and you subtract the smaller term, always it will be a positive number or not. So here also, rho minus sigma will be positive. It means if this is rho minus sigma positive, it means your terminal velocity will also be positive. Terminal velocity positive means body will keep on moving downwards. Terminal velocity positive means body will move downwards. Greater. So rho minus sigma will be negative. Terminal velocity will be negative. Body will move up. So what down. Why? Because density of body move upwards, right? It always move upwards. So if it always moves upward, then it means density of air is less than water. That's why it is able to move upwards. Fine. So let me repeat all the terms which I have mentioned, then note it down. See, once a body falls down, freely falls down without any external force in a viscous medium, a constant velocity is achieved, which is known as terminal velocity. Gradually, velocity will increase, and a terminal velocity will be obtained. You derive the formula for it by using this equation: Fv plus Fv is equal to W, weight of the body. Put in all the values, get the final formula as 2 by 9 r square g rho minus sigma by eta. This is the formula that will determine terminal velocity. If terminal velocity is positive, that means rho is greater than sigma. Density of body is greater than density of liquid. Your body will move downwards. If terminal velocity is negative, that is sigma is greater than rho, density of liquid is greater than density of body, your body will move upwards. First tell me, all these points are clear to all of you? Yes, no, what? Any doubts?
Yes, Miss.
Yes, ma'am.
All right. So do one thing, note down these points while writing also. If any point is there you're not able to understand, let me know. And from terminal velocity in your examination, this graph is asked and is asked to explain. So you'll have to explain that because of terminal velocity, you are getting such kind of graph that it becomes constant. Then we have numericals that we'll discuss right now only after this. Did you all write it till here or you were writing from here? Should I scroll or let me keep this page like this?
Set here itself.
Fine. So see here, one question. Let's practice on this topic. A water drop in air has a terminal velocity of 100 meter per second. Now, 8 such water drops combine to form a bigger drop. It means 1, 2, 3, 4, 5, 6, 7, 8. All these 8 drops are combining to form a bigger drop. Right? You have to calculate the terminal velocity of this bigger drop. You have the terminal velocities of these small drops, 100 meter per second. But for bigger drop, we do not know. So let's find a relation between the radius. Let's say the radius of small drop is R and the bigger drop is capital R. So volume will remain the same. The volume of 8 drops will be exactly equal to the volume of one big drop. So when you equate it, when you equate both, then 8 times 4 by 3 pi r cube becomes equal to 4 by 3 pi capital R cube. So 4 by 3 cancel, take the root, 2r becomes equal to capital R. Now see here, when we have the relation Vt is equal to 2 by 9 r square g rho minus sigma by eta for the smaller one. Do one thing, see everything is constant, 2 by 9 is constant, acceleration due to gravity is constant, rho minus sigma is constant, eta will also be constant. Nothing is changing in this question. So terminal velocity is directly proportional to radius. So terminal velocity is directly proportional to radius. It means V smaller is R square, V bigger is capital R square. Put it the relation of capital R square from here. So V smaller by V bigger. This becomes R square by 4R square. That means velocity of bigger drop is 4 times the smaller drop. So velocity of bigger will be 4 times smaller. Smaller is 100. That is 400 meter per second. This is the final answer. Just because of volume is same, we have this relation. Note down the question, note down the solution of it. Some more topics are there that we'll discuss. See, there are certain types of fluid flow. Fluid flow means a pattern through which the fluid flows. So see, there are certain assumptions while discussing fluid flow that fluid should be non-viscous. This is the characteristic of an ideal fluid. But in reality, we know every fluid will exert some viscosity. It will be compressible. Some things will be there. But this is the conditions or characteristics of ideal fluid. So it says that fluid should be non-viscous. It means no internal friction between the layers of fluid. It is incompressible. Density is constant. Fluid should be in motion. So this first type of liquid flow that we get is known as streamline flow. Streamline flow means if all the liquid particles at a given point follow the same speed. This means, see, this is some path. At this point, the velocity is, let's say, 3 meters per second, A point. At this B point, velocity is 2 meters per second. At this C point, velocity is, let's say, again back to 3 meters per second. If all the drops of the fluid or all the particles at this particular point are having 3, at this particular point are having 2 meters per second, at this particular point are having 3 meters per second, means exactly at all, and on that point, velocity is remaining the same, speed is remaining the same. We call it as streamline flow. All right. Then you have laminar flow. Laminar flow means liquid forms a series of parallel layers like this. Like this, layers are parallel where one layer cannot cross each other layer. This is known as laminar flow. And the third type of flow is known as turbulent flow. Turbulent flow means disorderly flow, like this. Like this. This is turbulent flow where direction is changing, points are crossing, like this. Now see, there has to be a space between these. There has to be a particular space between these two. Reason is that if at this particular point, two lines are crossing each other, so what will happen? Direction is given by tangent. Here also direction will be given by tangent. So velocity will be having two directions. That's why we usually do not intersect it. So when disorderly flow is there, velocity keeps on changing. It means turbulent flow. So rate of flow means volume of a liquid that passes the cross-section area per second is called rate of flow. Means amount of fluid. Let's say you have a pipe. In this pipe, let's say here, this much amount is entering exactly in 1 second. Then again, this much amount is entering in 1 second. This much amount is entering in this second. So what we'll say, let's say this is 3 liters. So 3 liters is entering exactly here. So you will say 3 liters per second is the rate of. All right. Why did we do all these terms? It's just that in the upcoming terms, and especially in your Bernoulli's theorem, we have to apply these. First, note it down. Then you have two important formula, critical velocity and Reynolds number, that we'll do, and some questions on it. First, note these points. See, Reynolds number is just a parameter to determine whether the liquid flow is turbulent, laminar, or streamline. So this is a formula. You just have to remember the formula. No derivation is there. Density of the liquid multiplied by velocity of the liquid multiplied by diameter of the pipe. Diameter of the pipe through which the liquid is flowing, divided by the coefficient of viscosity. This is divided by the coefficient of viscosity. Now, when you put in all the values, you'll get the value of Reynolds number. If this comes out to be lesser than 1000 or equal to 1000, then it means the liquid flow is streamline or laminar. If this is greater than 2000, then that is turbulent. And if it is in somewhat between 2000 to 1000, if when you solve it, you'll get the value, then it means it is shifting continuously. It is shifting between streamline and turbulent. So this is continuously shifting between streamline to turbulent, means sometimes streamline, sometimes turbulent, then again back to turbulent, back to streamline, like this is how you determine. So if the question directly comes, this all data, these all data are provided, tell whether the liquid flow is turbulent, streamline. So you will have to calculate it, whatever, let's say the value comes out to be 1050. So 1050 is lying between 2000 and 100. It means it is shifting between streamline to turbulent. This is the Reynolds number. Fine. Note down this Reynolds number. See, critical velocity is the velocity of the liquid flow till that value the liquid flow is steady. Means it is streamlined, steady flow is there. After this critical velocity is crossed, the flow of fluid becomes turbulent. So again, how do we calculate? These are not very important. Reynolds number and critical velocities are not very important. But if a question comes, directly formula-based question will be there because no derivation is there. So this is a constant K that we use. Eta, that is the coefficient of viscosity. Rho is the density and capital D is the diameter. Eta is what? Eta is coefficient of viscosity. Capital D is diameter of pipe. Rho is density. Here rho is density of liquid. If you wish, you can write it as sigma also, the way we write. So critical velocity is what? This is certain velocity, value of velocity. Fine. Different steady flow will be there of the liquid. Once this is crossed, now here the flow becomes turbulent. Here flow becomes turbulent. This is all about critical velocity. So if velocity of the fluid is less than critical velocity, your flow will be streamlined. If velocity of fluid is greater than critical velocity, it will be turbulent. All right. Hurry up, note it down fast. Text me done, then I'll stop the class.